Hello, my name is Henry Lee, and for the week 3 video, I'm going to talk about backpropagation. If you recall from the last video, we covered gradient descent, and in which we measured the accuracy of a neural network. The example that we watched was a handwritten image recognition, and we learned about the cost of a training sample, which is the sum of the square differences of each output. Meaning, if the actual value is a 4, it should have a value of 1. And so you subtract it from 1, and all the other ones that are not activated should not have a value, so 0. And we compare this against the values that we got from running the image recognition uh, software, which, for example, if it's like nearly bright, it would be like a high or like a medium size activation value, like a dark, like a low activation value, and like high activation value. And we want to lower this cost because the cost is measures inaccuracy. So the lower the cost, the more accurate it is. And we lowered this cost by finding the gradient descent, which we learned in the last video was the direction of the greatest amount of change. So in what direction we'll be able to make like lower this cost dramatically? And this is the result of like finding the gradient descent, and we have these directions. What these gradient vectors tell us is how much we need to change each weight and bias to achieve the lowest cost possible. So for example, for this value, you will have to increase the corresponding weight to like a small amount. For this one, you will increase the weight by like a relatively high value. For this one, you lower it because it's the opposite direction by like a high amount, and so on for each corresponding weight until like you get the lowest value possible or the gradient descent. This also the vector also tells us which weights and biases matter more towards the overall calculation. Like these high values are matter more. So if you change this, but you don't change like the small values, like it won't really matter because like they're very small. This one I'm gonna change it more. So how do you find the gradient descent? Well, imagine you get like a low activation or like a low predicted value compared to the actual value, which is it should be a 2, but like it's not bright, it's not activated. To increase it, we have 3 ways. We could increase the bias, so like it increases the value during the calculations of the activation, or you could increase the weight, like according to the formula. If you have activations here, you multiply by a higher weight to get like high value, or like the other way, you could increase the activation to increase the weight, or like no, to increase the overall computation the product. Increasing the weights for the neurons that are most active cause the most change since they have value. Like, for example, this one, like the white ones, because they have high activation values. If you add up like also like a high weight and high value will give like a very high product. Increasing the activation will have a similar effect, but we can so we can increase the weight, but we cannot increase the activation. If, even though like we could increase the weight or we could change the weight, we cannot change the activation because the activations are are calculated from the previous layer. We don't have direct control over that. Like weights, with weights we could freely change it, increase it, or lower it however we want. But activation they depend on the calculation on this formula, but like with the previous layer. So each neuron will have its own list of changes to apply for the previous layer. Since this is only one, there's actually more than one. So this whole column will correspond to one active neuron. This second row or second column to another node. This third one to another activation or to another neuron. So it will add up like all the list of changes for each neuron to apply in the previous layer. Because the values of a layer are used to calculate the changes in the previous one. They add up all of this. We repeat it from layer to layer until we have the changes for all weights and biases. So this is only from the final layer to the second to last. We also have to keep in mind the changes from the previous layer to this layer and all the way to the first layer. Because we span backwards, you can see the connections here, we call it backpropagation. And if you still don't see how we could get uh, gradient descent from backpropagation, the next image will make it clear. Since we have the list of changes that we want uh, for all of this, or like we calculate all the changes for all the weights and biases, we could put them in a table where like these are weights. So weight 0, weight 1, weight 2, until we have all the weights. This is for like only one sample, which is the sample where we used to recognize the 100 and number 2, 100 and number 5, 105. If we put all the list of changes for all weights from one sample or each sample all together for all of the training data, and we average their values, we're gonna get this vector. And from this vector, we could just write it like here. And this is how we get the gradient descent vector column that we saw earlier. And another thing I wanted to talk is stochastic gradient descent. Since I mentioned in the previous slide that to find the gradient descent, we needed to find the average for over all the training data. This could get very slow because it requires like a high amount of computation. We could instead we could split the training samples into mini batches and apply the changes part by part. So we only apply the changes here, and then after that we apply the changes here and apply the changes here. This is a much faster way of getting to the gradient descent, where we just take step by step instead of like doing like a whole straight line. We could just like slow steps until we actually uh, get to the lowest cost value instead of like waiting to get the, the longest path but direct path. Thank you. Hi. For the next part, I'm gonna be showing you guys a neural network simulator made by TensorFlow Playground. As you can see, we have like a simulator with neurons and layers, and we could like change the settings to play around with it to give us different results. For example, we could change the problem that we attempt to solve using a neural network. We could increase the data, the training to testing data ratio. So if we put it to 90% training data to test data, you will see that there's a way more training data than the testing data, which is the one like with the black outlines. Or we could increase the noise to make it harder to identify, because if more spread out, like for example, if more mixed, there's blues around the oranges and oranges and the blues. And batch size is just how much training sample it uses for one training iteration. And with these features, we are also able to make it identify the more complex shapes. For example, like that, you know. So with this shape, it will attempt to like paint it over the corresponding colors. So if we run it, it will see it was just a circle because this is simple. But for more complex problems, for example, the spiral, we have to change more to get this. And we can also change the learning rate, which is how fast it learns from the training sample and applies it to the testing data. Uh, and activation, we change the value or sigmoid and the problem type. Since this is a classification, because we only want to know whether it is blue or orange, it is a classifier. And let's attempt to see with the spiral. What the training loss means is like the misclassify data samples. But for this one, it looks like it's not gonna do very well. It's just gonna be around this level. So we want to add more neurons. For example, it doesn't necessarily make it better, but it could. And now let's try. Well, the training loss is about the same or similar, so I don't think it's gonna be that much better. Let's see, more training over testing and in bigger increments of testing. Okay, that looks much lower, like about half. Oh wait, it might actually be closer to zero, get close to zero. Okay, that was pretty good. And so that's how you play around with it. Thank you.